So I direct path to you. Thank you very much, and have hope you to have a great presentation. Tim Broad, please.
Thank you. Let me just share my presentation real quick.
Good.
And hopefully that's visible to everyone. Hello, everyone. I'm happy to participate in Japan Jamboree number 80. That is quite an accomplishment. We've been holding this Jamboree for, gosh, I don't even know how many years, but it's been very great to be part of this. And I'm going to talk about the status of embedded Linux and the Linux community. And let's see here. Let's see, it's not, for some reason, this is not advancing for me. Just a sec. No, that's not right. There we go. Okay, so just the nature of this talk, if you've never seen one of these before, I think a lot of you have, but I periodically take a look at the status of embedded Linux, the kernel and the community. This talk will be kind of a hybrid of different things. I'll talk about kernel technologies and some industry news. And I'll also give my thoughts on the overall status of the major technology areas and the embedded Linux ecosystem. So I hope to accomplish two things here. One is to let people know what's going on, and then also open a discussion on what's next, what needs more work. So embedded Linux, past versus present. First, let me go into the past. This is kind of a hallmark year for us. And so we're going to cover the history a little bit, talk about the bulk of the talk is about the present, and then I'll ask the question, are we done yet? So I started working on embedded Linux at Lineo, small embedded Linux company in 1998. So that's quite a few years ago. It's over 25 years ago. And then in 2003, I was hired by Sony to help start the Consumer Electronics Linux Forum. In 2005, we started the Embedded Linux Technical Conference, and that has become Embedded Linux Conference to this day. And then in 2010, Self became part of the Linux Foundation and eventually turned into something called the Core Embedded Linux Project. So in the early days, I spent a lot of time working with Linux in the 90s, even before I got into the embedded space. And we spent a lot of time trying to convince companies that Linux was suitable for embedded devices. So the competition back then was Vertex, VxWorks, PSOS, Nucleus, Microitron. So basically a lot of commercial RTOSes. Open source really hadn't caught on like it has now. And back then, the architecture support started with Intel. It was Intel only to start with, and then ARM and then MIPS were added. But no major chip vendor wrote the architecture support. So it was all community developers or just embedded Linux companies. And so the embedded distros, your choices were really kind of roll your own, or there were three companies at that time in the 90s and early 2000s, MontaVista, Lineo, and TimeSys. And Self spent a long time analyzing and trying to address deficiencies in Linux to make it suitable for embedded. In 2003, we identified 5 key areas that needed work. So system size, boot time, power management, real-time, and security. And so Self actually funded the contribution of several features in the Linux kernel in these and other areas. So we did actual work in a lot of these. We also did work in areas like file systems and other features. But in 2008, I can remember hearing Andrew Morton, one of the chief kernel developers, ask in a talk, "Are we done yet? Seems like we should be done with embedded, with all the features needed for embedded." And that talk is actually still available. It was recorded at ELC that year, so you can go look at it. So I'm going to come back to that question later, but let's talk about what's going on with Linux today, and maybe we can answer that. So my outline for this portion of the talk is that I'm going to talk about the Linux kernel, different technology areas, give some industry news, a little bit about the status of the community, and then I'll discuss kind of scorecards for some of those areas that Self tried to focus on and give some conclusions. So let's talk with the Linux kernel. So actually, it's been quite a while since I've given this talk. I used to give it quarterly, but I'm going to cover the versions in the last year. So since I think July of last year, I'm just going to pick a few items from each release that I think are kind of interesting and relevant to embedded. There's lots and lots of changes that go into every kernel release, a lot of things that are not really very relevant to embedded. And this talk, but I'm going to try and focus on the things that I think might be interesting for embedded developers. This talk is not very good at coverage of SoC or driver contributions. There's just too many of those to track. Every release, the semiconductor vendors and different companies who have hardware and peripherals related to Linux add probably hundreds of drivers. Every release, there's lots and lots of drivers. And then I'll also talk about development stats. So here's what's happened in the last year. Since July of last year, we had the 5.19 kernel that took about 70 days. Then the 6.0, so people thought it might be 5.20, but by the time it gets to about 20, Linus decides to update the major version. So 6.0 was in October, 6.1 was in December, 6.2 was in February, 6.3 was in April, and we're currently in the middle of the release cycle for the 6.4 release. So we're currently on release candidate 3, and we expect 6.4 to be released by the end of June. Notice we're continuing with a fairly standard cadence. The time period for a kernel release is usually either 9 or 10 weeks, depending on how many bugs are found and how many fixes, but it's been very, very consistent. The kernel, and it's been consistent like this for the last probably 5 or 6 years. Very, very consistent timing. All of the maintainers and Linus kind of know how to apply their patches and get things done in just a 10-week period. And you'll see when we get to the stats, it's a lot of code that's getting changed over that 10-week period. So let's back up though and talk about in July of 2022, Linux 5.19. What are some of the things that happened in that one? So there was support for the A.out executable format. That's a very old Unix format for executable files, binaries. That was actually deprecated in the 5.1 release. So a couple of years ago, it was deprecated, and they finally actually just removed it. So old binary formats are getting removed. The EROS, the extended read-only file system, now uses the FS cache layer, so it gives better performance on some systems. There's something called packet drop annotations that was added, and I'll talk more about those a little bit later when I talk about networking. You can now embed something called a boot config file directly into the kernel image. And in this release, there was initial support for the Lung Arch CPU architecture. And I'm going to come back and talk about that CPU architecture. I actually, I'll come back, like I said, and talk about that a little bit more. So I do want to talk about boot config, though. This is kind of an interesting feature. What this does is it allows passing arguments to the kernel as structured name value pairs. So boot config uses a simple text file syntax. It's similar to what you might see in like a shell script or a very simple configuration format file format. You can attach that either to an initRD image, or you can embed it directly with the kernel image. So the reason what this is useful for is passing a large number of tracing options. So if you try to do boot time tracing, which you might be very interested in to see how drivers initialize, or if you're working on improving the boot time, which is very commonly done in embedded systems, you probably want to apply a bunch of ftrace options. Well, the ftrace options consists of events, filters, actions, probes, and field declarations. you can easily surpass the allowed size. I think the allowed size for the kernel command line is probably about 4K, but if you're setting up a very complicated tracing system, it can take much more than that. So this was added in an earlier version, and now in recent kernel versions, there's more flexibility for how you can pass this to the kernel. And so that's an interesting thing that you want to be aware of if you're going to be doing boot time tracing on a more recent kernel. In Linux 6.0, IOU ring supports zero copy network transmissions. So there's been a lot of work with a new system called IOU ring to make it highly performant. Interesting note, running K-unit tests now taint the kernel. So if you run a K-unit test, it will set a flag indicating that the kernel is not kind of in a pristine condition. Some of the unit tests can do operations which may disturb a production system. So you may want to, in a production system, make sure that you have not executed any K-unit tests, and you can detect that now. The runtime verification system was merged, and this is a system that allows you to do some validation for some of the state transitions in the kernel. So moving towards, this is particularly interesting for people doing safety critical work. The config Android config option was removed. So there used to be this config option used to indicate that the kernel was being built for Android. But it turned out that a lot of people kind of misused this option, and so the kernel developers thought it was better just to remove it and replace it with configuration options that were specific for the things that this controlled. So there had to do with some things related to power management and some other things. And then there was a printk pull request was rejected in October. So the developers have been trying to refactor printk for a while now for real time and for other reasons, for better performance on SMP systems. It's a big change that's been in the works for several years, and unfortunately that got rejected and they had to go back to the drawing board. In Linux 6.1, there was support for destructive BPF programs. So BPF stands for Berkeley Packet Filter. So Berkeley Packet Filter programs normally are put in a sandbox and they're not allowed to do anything that will crash the kernel. But in the 6.1 release, that was changed. So a BPF program can actually crash the kernel. And the reason for that is that it allows a BPF program to create a crash dump, which is very handy for debugging a kernel. So this is intended as a special use case when you're using BPF to diagnose what's wrong with the kernel. Then BPF, if it detects something that's really bad, or that a developer may want to examine, it can actually crash the kernel. There was in 6.1, there was experimental support for Rust language added so that people can write drivers in Rust. There was an improved top-level page for the kernel documentation. The kernel documentation actually looks quite nice now. And then there's some support for multi-generational LRU, least recently used page algorithms. And this collects pages into groups by age, kind of as its name implies, multi-generational. So there's several generations of ages that pages are grouped into. And this can help with performance on the virtual memory system. In Linux 6.2, the slob allocator was deprecated. So there are several different memory allocators inside the kernel. There are three primary ones that handle fixed size buckets. The slob allocator, the slab allocator, and the slub allocator. I'm going to talk more about this later when I talk about system size and kind of the implications there. More Rust infrastructure code was added. There were improvements to SquashFS, and there's actually been a new tool added to the system, to the Linux source code, that can be used to control the operation of the runtime verification system. So there's a tool with you can use several arguments to manage the models that you use for runtime verification. In 6.3, so this is the actual last released kernel. The other 6.4 is still in development. The 6.3 kernel in April, there were lots of old unused board files that were removed. Support for old ARM boards and old ARM processors. Another interesting thing is the kernel can be configured with a built-in drystone test. So I thought this was really interesting. K, I don't know if this is down inside the K-self test directory or where it was put, but you can actually run a drystone test inside the kernel, getting rid of any user space overhead for that operation. And that's the first time I've seen kind of an external test that was kind of a user space test taken and refactored and put directly into the kernel source code itself. The default make v equals 0 option has been removed. So you used to the capital V was used for specifying the verbosity level. You could make a quiet build with this, but the upstream developers do not want you doing quiet builds. They want you to do noisy builds so that you can see if any warnings pop up. This would suppress any warnings from the compiler. And so that actually has been removed so that now warnings will always come up. And this is helping developers to have an incentive to make sure that their code doesn't cause any warnings during builds. So major improvement to the build environment or the build results. To be able to compile with no warnings, it's very helpful. There was a minor change to the developer's certificate of origin. It clarifies that nicknames can be used for contributions, and I think I actually cover that again later. Oh no, I think this is the only place. So as long as your identity is known, oh yeah, I think I do cover it two places. Okay, so in this release, Linux 6.4, we've already had the merge window. That was at the end of April and the beginning of May. So they actually went ahead and removed the slob memory allocator. So it was deprecated in 6.2 and removed in 6.4. And again, I'm going to come back and talk about that. There's actually some nice documentation added for building the kernel. If you've never built a kernel before, they continue to add kind of nice features to the documentation. This is how to quickly build a trimmed Linux kernel. This is for a desktop system, so they don't really cover cross-compiling, but if you're new to the kernel, they have some nice documentation that's making its way into the kernel docs, and it's all online, and it's updated whenever the kernel docs are updated in the source code. So it's the documentation can be considered live and up to date. There's something in the code. There was a macro used for modules called module license. And it turns out that all of those declarations were removed for code that cannot be built as a module, which seems to make sense. There's a long explanation for why people were using this macro even in code that could not be built as a module. And they finally fixed the issues involved with that and got rid of it in quite a large number of places. And this actually helps with tracing the real license for a lot of the code that's in the kernel. Most of it is GPL v2, but there are exceptions. There are dual licensed code, and there were some other things. And then another thing is that user trace events. So user trace events was actually merged as a feature, but there were some API fixes required for it. So it's now possible to use the kernel to trace user space. So you could always do things like strace, where you could trace system call interactions between the kernel and user space. but now you can trace into programs using the kernel, and that's very helpful. You don't have to set up a whole debug system like GDB to figure out what's going on with a user space program. So I wanted to circle back and just talk about LungArch. I didn't list it, but basically LungArch started going in 5.19, and they've been putting little bits and pieces of it in over the past whole year. So each of those releases from 5.19 all the way through 6.4 has gotten some more support for this architecture. So it's a processor architecture by a Chinese company called Lungsun, and it's actually not a brand new architecture. Well, it's relatively new. So the original architecture that's based on started in 2002 as a variant of MIPS. And over the years, this company has modified it, and they finally came out with kind of an updated, newer release of the ISA, the instruction set architecture, that was released in 2021. So that's actually pretty new as far as instruction set architectures go. It has incorporated ideas from both MIPS and RISC-V, but its instruction set is different from both of those. So it's not binary compatible with either of those systems, but it's trying to use ideas from both of those RISC-based instruction sets. It supports a 32-bit reduced instruction set, a 32-bit standard instruction set, and a 64-bit instruction set. And it's basically been designed with Linux in mind as the primary OS target. So it's an interesting case of the instruction set being designed for Linux rather than Linux being designed for the instruction set. The reason I mention this, I don't think that this is going to be used very much in embedded. It may be, but it looks like it's kind of more geared towards data centers and stuff in China. The reason I think it's interesting to note is that, to my knowledge, this is the first kind of regional specific instruction set architecture. It seems very much based on kind of the Chinese market and the Chinese vendors and suppliers. And so I don't know if we're going to see it in other regions of the world. It may as China starts exporting devices, but it's very, very interesting. I think it has the support of the Chinese government, and it's basically intended to make sure that China is not dependent on foreign countries for their computer resources. So that's kind of an interesting aspect of this architecture that I don't think other architectures have. Now, turning to developer stats, I actually have quite a bit of developer stats just to give you an overview. I covered both 6.1, 6.2, and 6.3. But just looking at, I show kind of active developers by chain sets and by change sets, which is number of commits, and by lines, and kind of the areas they're in and what the organizations are of the companies that are working on stuff. So if you look at the top contributors, so in 6.1, we had over 2,000 developers, and over 300 of those were new developers, so people who had their first time patch. Of course, people who had their very first time patch are not in the top contributors, but it's very interesting that there's always a set of new developers working on Linux. And the number of change sets per release are very consistent. The number of developers and even the number of new developers seems very, very consistent over time. So here's just a list of the active developers in 6.1 by change sets. Krzysztof Kozlowski of Linaro had 221 change sets, and he was working on device tree updates. I thought it was interesting that we have two people from Huawei in the top 5 contributors, Ying Liang and Zhenqiao Shao, working in different areas, cleanup work in device drivers and the networking subsystem. And then Andy Shevchenko from Intel did work all over the driver tree, a lot of different drivers. and Johan Hovald from Lenaro. Again, so you see Lenaro has two people in the top five there. Again, with driver fixes and device tree changes. If you look, so that was by change sets, the number of commits. If you look by active, number of lines of code change, then you get a different picture. So a lot of people work on a big change, and it may take a year or two before they decide to attempt upstream it, and it may have gotten quite large at that time. So Liam Howlett of Oracle has been working on a new data structure for the tree, the maple tree data structure that's replacing some of the other tree structures in the kernel. And 86,000 lines of code in one release. So that's a very big change. So he's changing, not just introducing this new maple tree data structure, but also he has to change a lot of the users of the old data structures. I think this is replacing red-black trees. And then you have Frank Min from AMD with 56,000 lines of AMD GPU register definitions. And that just goes to show you that GPUs have lots of registers. They're just super complicated, GPUs are. And Ping Ke Shi from Realtek with wireless network driver. Ian Rogers. This is another one I thought was interesting. Event definitions for perf. So Intel just has a bazillion of these event definitions, kind of different processor events that the perf tool can report on. And so you can get 12,000 lines just doing event definitions for the diagnostics tool. And then this last one, Stephen Heminger, turns out I thought he was with Microsoft, but I double checked, and looks like he's retired, but he's still working. And he removed support for DECnet. So he had 12,000 lines. Almost all of those were removable. And so you can actually make the top contributor list by taking lines out of the Linux kernel, which I think is really interesting. And we're going to see a pattern here. That's going to be more common. So looking at the 6.2 developer stats, again, this one was in February. We see a few more change sets, 15,000 as opposed to about 13,000. Again, around 2,000 developers, around 300 new contributors. And in different areas again. This time you see Pengutronics, and the reason for UA Klein Koenig, the reason for this huge number of chain sets was just he was fixing an issue with the driver subsystem, and he had to refactor. He made changes all across the kernel. We're having a little bit of interference, so maybe someone needs to mute. And then Krzysztof Kozlowski, again, with device tree updates. Johan Hovald was back with Qualcomm PHY drivers. Andy Shevchenko was back with cleanups in driver tree. And then Thomas Gleixner, who's a pretty famous name, core kernel in x86. And then by active lines of code changed, Ian Rogers came back again with 149,000 lines of PMU event definition files for perf. Ping Ke Shi again with more wireless driver work. Ben Skeggs for a graphics driver. Steen Hegeland with a network driver, and another person, Arne Bergman, removal of unmaintained drivers. This is Arne Bergman from Lenaro removing a bunch of ARM code. Finally, 6.3. Again, 14,000 change sets, 1971 developers, 250 new. So a little bit smaller release than 6.2. But again, Christoph is in the top top 5 again. Arne Bergman is in the top 5. Andy's in the top 5 again. Christoph Helwig, who's usually in the top 5, looks like he took a break over the winter, but he's back and refactoring the block and file system code. And then by most number of lines, so this is Arne Bergman of Lenaro, 160,000 lines of code removed from the ARM tree. Kali Valo, the Qualcomm Wi-Fi driver. Greg Kroll-Hartman did a bunch of driver work, but most of his lines were from removing a driver from staging. Hans Verkiel of Cisco removed old media drivers, and Kai Huangqing removed lots of DRM drivers. So in the 6.3 release, 4 of the top 5 developers on the top changes list were there because they removed code instead of added code. So there's actually quite a bit of churn going on this year with people removing a lot of old and obsolete code. So just taking a quick look, these numbers are a little bit different than the previous pages because I used a different tool to measure them. But if you look, we're pretty consistently getting around 14,000, 15,000, 16,000 commits and around 2,000 developers, 2,100 developers. It's amazing, given that there's 300 new developers every release, it's amazing that the numbers are so consistent. The last thing I want to talk about is kind of most active organizations and what areas they're working on. So if you look at who are the employers or who are the organizations that are providing the most developers to work on the kernel, you have in the core kernel, which is kind of the core systems, the memory management, the scheduler, and things like that. You have Google, Oracle, Huawei, Red Hat, Meta, and Intel. And these are organizations that have over 5% of the total contributions for the entire last year. So that's all the way from 5.19 through 6.4. In the Arch directory, not huge surprises here. You have Linaro doing a whole bunch of ARM work, Google and Intel doing a bunch of x86 work, and then IBM doing work in other platforms. And then unknown is people there's a whole set of developers who are working on architecture support who we don't know who their employer is. They either could be hobbyists or they're just using an email address that is not affiliated with an employer that we know. And then so drivers. So drivers is the biggest subsystem in the kernel. There's literally thousands of drivers, and people are always working on adding new drivers for new hardware. You have Intel, AMD, and Linaro shows up there again as well. And then unknown and none. So there are people who are known to not be affiliated with any company. So actually a large group of people just come in and do a driver, and a lot of those are hobbyists or volunteers. So they may work for a company, but they're not doing the work on behalf of their company. And then the file system and block layer, Red Hat and SUSE, so those are distribution vendors. Oracle, obviously working with database stuff. Meta, Huawei, and a lot of consultants are in this layer. And then in networking, you have Intel, Red Hat, Google, Meta, Unknown, and NVIDIA. And then interestingly, documentation, you have a lot of unknown and none. So each of these lists is sorted from left to right by the highest contributor. So there are more unknown people than anyone else working on documentation. And that is actually an interesting stat that for a lot of developers, their first contribution to the Linux kernel will be in the area of documentation, as they find something that's an easier place to fix than in the coding areas. But you see that some of the big companies, Google, Intel, Red Hat, Meta, and Lungsan, I assume that Lungsan is adding documentation about their architecture in there. So that's just interesting data, I think, to see who's been working the most in the kernel. Okay, so the next portion I want to cover is technology areas, and I'll kind of pick up the pace a little bit. There's a lot of stuff here, but I'm going to try and go not super fast, but fast enough that we don't get bogged down. So I already talked about LungArch support, so architectures, that was added. But actually the bigger discussion is that more stuff is getting removed. So support for many old ARM boards was recently removed. That was all that work by Arne Bergman. And they have proposed, the kernel community has proposed the removal of some old architectures, in particular Super H, which is Super Hitachi, the SH instruction set architecture, and Itanium. And so these are under discussion. If you care about these being maintained in the upstream kernel, you should go onto the list and make sure you participate in the discussions. There was a big community discussion about this, how long to keep code in the kernel. And the answer seems to be as long as it's not bothering people, if it's not imposing a burden for other maintainers of other areas, it usually will sit there. Some of these have not seen active maintenance for years and years. So, and if someone cares about the latest kernel enough to step up and maintain it, if there's a maintainer for it, people will let it stay in the kernel for years, even though it appears that the hardware is no longer being sold or whatever. So it can stay a long time, but for like this Super H and Itanium and like these old ARM boards even, there's just no one willing to maintain it, and it just becomes more burdensome as people try to do changes that affect the entire kernel. There's a lot of maintenance and a lot of effort, and doesn't seem like anybody cares. So these architectures may get removed in the future. In terms of bootloaders, just two quick things. U-boot, which is probably the most popular bootloader in embedded Linux, now supports loading images over HTTP. So previously, U-boot only supported the UDP protocol, did not support TCP. And so you could only use NFS or TFTP as servers. So both NFS and TFTP use UDP instead of TCP. But now U-boot has a full TCP stack, and you can download the kernel and other images that you need, like the device tree blob or the initRD, from a web server. So this actually allows much more flexibility. There's actually a wget command inside U-boot. And so that's actually really interesting. A lot more flexibility in where you get your kernel from. And so that's an interesting new feature for that. Another kind of bootloader related feature. This is not a bootloader itself, but there's a set of tools called SnagBoot that was produced by Bootlin. And this is used to help recover boards. There are all kinds of kind of proprietary tools that are used on various boards to reflash them, to recover if they won't come up, if they get stuck in like the bootloader. And so Bootlin kind of I think they got tired of dealing with this huge different set of tools on all the different boards they work on. So they produced this project, which is open source. It consists of two main pieces, one called Snag Recover, which initializes the memory and runs your bootloader, and it knows how to communicate with the board over USB or a serial port or whatever. And it can deal with a lot of different bootloaders, mostly U-boot, but it can deal with other ones as well. And then Snag Flash, which is used to flash a working system image. And there are several different industry standards here. There's something called DFU, which is Device Firmware Update. A lot of systems use USB mass storage or fastboot. A lot of these boards don't use an SD card, or if they do use an SD card, it's hard to work with. So this is a single tool that works on several boards and replaces a whole bunch of different proprietary tools. So bringing some standardization. So you can read about that on their blog. Very handy tool, I think. In terms of the core kernel, not a whole lot going on in the core kernel. I said the PrintK refactoring was kind of sidelined for a while there, but something did come up at the kernel summit. One of the developers is working in IOU ring. So IOU ring is used mostly for IO, for asynchronous IO. So user space does not have to make system calls in order to perform a sequence of IO. But they're starting to use it for other things as well. And in particular, one developer has come up with this thing called IOU ring spawn, which is, instead of just using IOU ring for reads and writes, you can actually do process execution. So it replaces fork and exec. So the normal way that you start a new process in Linux is using the fork call followed by the exec call. And there's some reasons it was structured that way in the original Unix. But this is way more efficient. It keeps all of the operations completely in in the kernel. The fork and exec system, the way it works, it was kind of, well, it worked good enough at the time, but it almost always discards the parent's code immediately. So there's a lot of reasons why there's inefficiencies in it. And so you can now use IOU ring. There are two new operations, clone and exec. And when you put those in your ring buffer, the kernel does both of those immediately. And it's been found to be 6 to 10% faster than vfork and about 30% faster than POSIX spawn, which is probably the most common one. So we may see some speed improvements in spawning executables coming in the future. So probably the data center guys are the most excited about this because they're spawning, you know, like 10,000 threads a second or something. But it's interesting nonetheless. In file systems and I/O, there's lots of tweaks to existing file systems, but not much specific to embedded. Just kind of usually the features are kind of on the fringes, not something that's going to affect your embedded products. In terms of languages, I want to talk about well, two languages. One is a variant of the other. First, MicroPython. So this is a version of Python that's specifically targeted at microcomputers and embedded use cases. And it just had a new release, a 1.2 release. It kind of languished for a couple of years though, but it seems like it's coming back. And it's a very, very small. I didn't put the numbers on here. I should have put the numbers on here. So regular Python is several megabytes, but this MicroPython is really made for microcontrollers. It runs much smaller. It's about 300K. The actual interpreter. And there's a new package manager that allows you to install packages from a repository. That hasn't existed before for MicroPython. It's got reduced code size. You can precompile the modules, and it adds support for many new boards, including support for Zephyr. And this was really interesting. You can actually target WASM or WebAssembly. So you can run you can compile the MicroPython interpreter for WebAssembly, run that in a browser, and then load Python apps. So you can now run Python apps in your browser. So that is actually pretty interesting, I think. And you may even want to do that. It sounds like something that maybe you'd want to do for desktop OSs, but I can imagine scenarios where you'd want to do that also just in embedded. So that's quite interesting. For Python, the big news was Python 3.11 was released this last year. The .3 release came in April, but Python .3.11 is, I think, a very big deal. It has a lot of big improvements. The biggest improvement is that it's much faster. It has better traceback. There's fine-grained error locations in the traceback, so it's easier to debug things. Claims to be 1.22 times faster on a standard benchmark suite. Depending on what app you're running and how it's structured, it's 10 to 60% faster than Python 3.10. So that's a huge jump in just one minor release. It's got some other things, exception groups and typing improvements. But anyway, if you're using Python, that's something you may want to consider upgrading. And then this was just weird, but it just shows you the world we're living in. So someone came up with this Wolverine project, and it's Wolverine named after a character in the X-Men comics who can self-heal. So this Wolverine program can run your Python program, and when a crash is detected, it'll actually go out to the internet, use GPT-4 to analyze the failure, to search for the failure online, find the solution to the failure. So we'll collect code and actually generate code that will fit into your program, apply the bug fix to your code, and rerun the program to continue detecting problems. So if you have, multiple bugs in your code that cause crashes, it'll detect the first one, fix it, and then keep running and detect the next one. So this is an example of AI being used to automatically fix programmers. fixed programs. So that's pretty interesting. We'll have to see how well it works over time. I don't think anyone's out of a job yet, but AI is making huge strides this year. So even in the area of debugging programs. And then Rust. Rust support continues to go into the mainline kernel. Has not been used for a real driver yet. So my own impression is I keep seeing more and more Rust being used all over the place, particularly by large companies like Google and Meta. So Google actually has a whole operating system, a secure operating system called Kata OS, that is, I think, provably more secure than some of the other operating systems out there. I'm not sure where they're going to apply this. I doubt it's full-featured enough to like run Android on top of, but they might be using it in other places that are either safety critical or that are high sensitivity, secure sensitivity. Just a minor note: Rust 1.71 will likely support the Musel C library, which is it's a much smaller C library. So that is interesting. Musel's been used quite a lot of places. And then another thing that is kind of lending some credibility to Rust is Google is using Rust a lot of places, and they've actually announced that they're publishing their security analysis of all the Rust crates. So a crate in Rust is similar to a module, or it's like a gem in Ruby, or a Python module, or an npm module if you're doing JavaScript. But anyway, so they've actually went out and audited all the crates that they're using, which is a huge number of them, and providing that open data to the community. So that means that you don't have to go and do that stuff yourself. In terms of networking, I did talk about this a little bit. So there's a new function in the kernel that allows you to give the reason that a packet is being dropped, and this was added a while ago. I think 5.19 was when this was first added, but lots more instrumentation has been done over the last year. About 300 different sites have been instrumented now. So this is very helpful for diagnosing networking problems. Real time. Got to talk about real time. Patches, the main thrust of real time, the preempt RT was added in 5.16, but patches have been going in continuously. So what's left in preempt RT? Well, last year we only had about 1,300 lines of code left to go in. This year we've got about 4,500 lines of code left to go in. So it actually grew. The patch set grew by about 30 patches. So they keep finding areas that need work. And the number of lines could be off because there's a work in progress in the patch set that I examined for print K. So it could be off by about 1,800 lines. But anyway, but there's still changes required to print K, the serial driver, and some core scheduler, and a whole bunch of other places, kind of little minor tweaks all over the place. So people are still waiting for the day when Linux RT will be fully up in mainline. I don't know if it ever will be. I think there's always going to be a set of patches that are pending, like any other area in the kernel. So I think eventually we'll get to the point where there's just a branch of the Linux kernel with the patches that are in progress. So I'm kind of wondering why it's still being done the way it is with a set of quilt patches. But in terms of security, kernel hardening continues. Okay, in terms of system size, just two quick things here. Actually, three. One on the next page. The slob memory allocator was removed from the kernel. So this was actually, this has kind of made me sad because the CE Linux forum actually paid the developer who wrote this and got this into the kernel. It's supposed to be the super low memory memory allocator, but not enough people were using it or reporting that they were using it, and no one was maintaining it. The original maintainer went off and started doing some other things. So this was deprecated in 6.2 and actually removed in 6.4. That's only 2 kernel releases. I just don't think that that was enough time for people to object. I don't know if you are using slob in any of your projects. then you should complain or step up to maintain it. But I kind of doubt that'll happen. I think it's probably just gone now. But if you are on Slob, don't move to Slab, as they're also the upstream developers are working on getting rid of that one. That's the original memory allocator in the kernel. Everyone, if you're gonna move stuff, move over to Slub, which is the latest and greatest. And there actually is, in order to kind of soften the blow of taking Slob out of the kernel, they made a new config Slub tiny option. So you can turn that on, and Slub tries to be as lightweight as possible, but it's never going to be as lightweight as Slob was. Slob was specifically designed for like systems with only 2 meg memory. And then this isn't new, but I just found out about it this year. There's a tool called Bloaty McBloatface, which is kind of a goofy name, but it's a size profiler tool, and it's been open sourced by Google and analyzes the size of binary images. And it does a very deep inspection of ELF and can tell you every line of code what it's related to, and how it got there, and what size it is. And so you can show a lot of different stats. If you go out to GitHub, Google/Bloaty, you can use that if you're doing system size work. And then the other thing related to size, which I thought was really interesting, is there's this thing called nolibc. It's actually been getting into the kernel over a period of time, but it's a minimal C library replacement that it actually shipped with the kernel code. So the thing that's crazy is it's not a set of C code. It's a set of header files, .h files with macros. So the macros, it actually, well, I mean, it turns into code, but it allows the creation of a very small static binary. So usually when you compile a program, you end up having your code and it's dynamic linked to a C library, either glibc or Musil or uclibc or something like that. But in this case, it's not. There's no library at all, and hence the name nolibc. It only uses these macros, and it goes directly to system calls with very, very little code in the way. And in fact, so if you look at my example here, hello libc, that is the size of just the printf that prints out hello world. It's 1159 bytes, but that's not including the shared library, which is probably about 1.8 meg. nolibc is smaller than that, statically linked. It's only 1100 bytes, and it has no libc, does not have a libc dependency. So the reason this is interesting for embedded is because there are people who use embedded Linux and only have like 1 or 2 binaries. And maybe they have BusyBox and they have their application, and that's it. So for very, very deeply embedded, this might be a really interesting approach to actually go without a C library at all. Okay, I'm going to pick up the pace. Test systems, I think I've talked about all these before. There's a bunch of ones that are reporting bugs to upstream. LTP, the latest release was just in May. They've added a new runtime test execution manager called Run LTP NG Next Generation. K-Self-Test just has a whole bunch more tests. Every year they add a whole bunch of new tests. KUnit is also being improved. ToolSanes GCC just had the 13.1 release. And you can kind of look at some of the features there. Notice LungArch support in there. So LungArch, when you get a new architecture in the kernel, you can't just do the kernel work. You also have to do the toolchain work. And so LungArch actually showed up in GCC and LLVM. I didn't have it on this page, but basically the 16.0 release of LLVM was released in March, and you can go look at the release notes to see what's going on with that. There's one tool I want to talk about, B4. It's now possible. This is very interesting. So B4 was originally written to be able to retrieve patches from the mailing list. But it was recently extended and augmented so that you can use it to submit patches to the kernel. So you do not have to submit your patches through a mailing list. Well, actually, it goes through a mailing list, but B4 handles all that for you. You don't have to have a mail client at all. And in particular, you don't have to fight with your corporate mail client. A lot of corporate mail clients, especially exchange servers, will mangle the messages and it causes all kinds of problems. But V4 allows you to submit, contribute a patch without using the email system. It kind of goes through a different mechanism. But then it does end up on the back end going through email, but as a client, you don't have to have email. It is a good idea to be subscribed if you want to contribute so you can respond to comments. You have to respond to comments. But that's very, very interesting. This is the first time that there's a non-email path to get patches into the kernel. Let's see. Tracing, I didn't do a whole bunch of study on this one. Perf always has a bunch of new features. If you're not using that for diagnostics on the kernel, you should be looking at it. And then eBPF can now be used for tracing. Okay. I think we're down to just two more of these technical areas. So the Octo project, BMW joined the Octo project. And so that's pretty big news. The latest version was released in May. It upgrades the kernel version, a bunch of recipes. They've improved memory and disk usage and recipe parsing time. A bunch of other things, improvements. So if you're using the Octo project, you maybe ought to consider upgrading to that. Okay, now the kernel community, just two kind of notes on this. So this one was kind of funny. So Linus Torvalds, I don't know if you remember, but he used to be known for having kind of harsh language, and he gave that up, and he actually wrote some scripts to help him catch whenever he was being kind of too harsh on people. So he actually wrote a script that before he sends an email, a script will scan that and catch any words or phrases that are inappropriate or kind of too harsh. He wants to be kind of a nicer, gentler Linus. And so what Linus writes these days is all very nice and friendly, but not all the kernel developers are doing that. And so he said his script was catching messages, but it wasn't his fault. And he asked the other kernel developers, please don't call each other morons on the mailing list. So apparently morons is one of the words in his list. He says, you guys have to clean up your act because I can't reply to your messages if you have harsh words in them. So that's a really interesting example of Linus's tools helping the entire community. He can't quote your text or your message if you have harsh language in it. There was a slight change to the developer certificate of origin. I already talked about that. You don't have to give your actual real name. You can give a nickname, but we have to be able to identify who you really are as a person. So it's still not anonymous. Okay, so that was technology areas. That was by far the longest section. Sorry about that. Industry news, I'll just go really quickly through a few of these. The Software Freedom Conservancy has sued Microsoft over Copilot. So Copilot is some code that is a service by GitHub that allows you to allows an AI system to recommend code to you. And the SFC said that the training data included GPL code, and it's a GPL violation if you reproduce code and you don't follow the license terms. And that's hard to argue with. In particular, the SFC gave some examples where the exact code from a GPL project was produced by Copilot. I mean, line for line, including the comments, which is clearly a derived work of the original code. So actually, this is just one of several lawsuits that were brought last year over AI and the training data that was used for AI. So it raises a lot of questions about the copyright interaction with training data for machine learning models. But that's pretty interesting. So Intel and ARM have an agreement on this is not Intel producing ARM chips, but this is Intel Foundry, which is kind of the processor, the fab business they have all these processes for making super small features on their on the wafers. So it looks like 18A is something that they've announced they're collaborating with ARM on. It looks like when they get down to 1.8 nanometers, or they're calling it 18A, the ARM processors will be able to use that. So a lot of ARM licensees are fabless, which means they are not using a chip fabrication um, and their own thing. And so it means that Intel can produce ARM chips, not for themselves, but for ARM partners. And so they're working together on that. I thought that was pretty interesting. Unlikely allies in the semiconductor business. NASA is actually putting together something called the High Performance Spaceflight Computer, and they have selected RISC-V for that, which is really interesting. So this is a RISC-V processor with 12 cores, 8 with special vector processing extensions, and then 4 general purpose cores. And I believe that these are in clusters, and a lot of these cores are being used for fault tolerance. And so and the interesting thing is NASA says that this can be used outside of space applications. So if it really does have the fault tolerance because of the duplication in cores, that'll be really interesting. A couple other interesting news. So Leonard Pottering, most famously the author of Systemd, left Red Hat and is now working for Microsoft. So that's actually that's interesting. So the guy who's in charge of the init system for all of Linux is now working for Microsoft. So Microsoft has hired a number of these open source and Linux leaders. Microsoft is doing a lot with Linux. They have Azure and Windows Subsystem for Linux, and so that's a big change. I just want to cover real quick. I can't help myself. I always follow stuff going on with Linux in space. And so I'm going to talk about the Mars Ingenuity helicopter and the Starlink satellite constellation. If you've been watching these, you know that I do this every time, or at least the Ingenuity helicopter. I think it's the most interesting embedded Linux system in the solar system. So that's pretty cool. So it's Mars helicopter. It's on Mars. It landed in February of 2021. They performed some initial demonstrations, and then after that demo, they planned only 5 flights, and it's still flying 2 years later. So far, it's performed 51 flights so far. The latest thing that they've done is autonomous landing site selection. When they first started flying it, they knew exactly where it was going to take off from and exactly where it was going to land. And they had scouted it out. They knew using the rover that it was all flat. Well, now the thing is flying up into canyons and it's completely autonomous. There's no real-time control because it's 30 minutes away, radio signals, and so NASA can't control it in real time. So it has to be completely autonomous. So they uploaded some new software that can detect the slope of the landing area and any debris that's there, large rocks or something, and it will adjust its landing position. It'll find a flat, clean area to land. It's amazing. It's doing all this stuff autonomously. It's truly amazing. Its main mission now is scouting for Perseverance. It provides pictures of areas of interest, and it also looks for navigation concerns for the rover team. They've left, both the rover and the helicopter have left the crater floor. The terrain is more rugged. They're actually going through canyons and stuff. And so it's quite possible for the helicopter to land somewhere outside of the communications range. And that is a very, very big problem because the rover commands are relayed through the rover. I mean, the helicopter commands are relayed through the rover. So if they ever get completely out of range of the rover, they can't communicate with the helicopter anymore. So they did a bunch of flights, 41 through 46, consisted of keeping Ingenuity ahead of the rover. The canyon was too narrow. If the rover got ahead of the helicopter, they wouldn't they wouldn't be able to catch up and go past it because they have all these rules about how close those two can be. They don't ever want the helicopter to damage the rover. Anyway, so that just kind of interesting stuff. There's the path. You can see it went up some canyons and stuff. And they're now looking at like another subcrater that's up in the delta that leads into the main Jezero crater. So they're doing all this stuff on Mars with Linux. That is totally awesome. And then there's some resources for that. And then the Starlink satellite constellation. I got to talk about this one. So SpaceX is using Linux in their rockets, their space capsules, and their satellites, including, I don't know if anyone's a space enthusiast, but including the test flight for their brand new one, their Starship, the one that got 39 miles up and then blew up. It was a test flight. They expected it to blow up. But anyway, each Starlink satellite, that's the rocket. The satellite cluster, there are now over 4,000 satellites in orbit. And so you can see that is an actual map of the satellites that I took today. And each satellite uses over 60 processors running Linux, and they use it for fault tolerance. And you could actually think of a Starlink satellite as essentially a high-end router, high-end data router that you might find in a telephone company, because that's what it's doing. It's relaying IP all over the globe from ground stations and then back down to user terminals and back. So that's amazing. There's literally in the tens of thousands of Linux processors up there. Okay, a couple of notes on the community, and we'll be close to wrapping up here. First, a sad note. So I don't know if you're familiar with Wolfgang Dank. He's the founder of Dank's Software, pioneer in the field of embedded Linux. Unfortunately, he passed away last year, October 14th, 2022. And he truly was a pioneer in the field of embedded Linux. Actually, his embedded Linux distribution, which was called ELDK, Embedded Linux Device Kit, was put out by Danks, and it was one of the first ones that was used in satellite. So he's been around for years and years. He's the creator of DOS U-Boot. So, and that's kind of a play on words. There's a movie called DOS Boat about U-boats. But he did early work in real-time solutions for Linux, was a real champion of open source, and he'll be missed in the community. In terms of conferences, Embedded Linux Conference is now only happening once a year. We'll be alternating between Europe and North America, so effectively only once per region every 2 years. So it'll only be in Europe once every other year, and North America once every other year. So for people who are not traveling, I mean, I travel, so I get to every year, get to all of them, but we may decide to fill in with regional events or with plumbers. So in the years that like Europe does not have an ELC, we may direct them to embedded recipes or to plumbers or something like that. Sometimes it'll be in kind of its own embedded open source summit umbrella event. And sometimes it'll be at kind of open source summit, the bigger Linux Foundation umbrella event. But the plan is to have it consistently in the spring, in April or May. The next one is just coming up next month, the end of June in Prague. And then in 2024, we already have the dates. It'll be in Seattle in the USA in April. So there's a bunch of other conferences related to embedded Linux. So there's Japan Jamboree, and I actually don't know. I need to talk to Ueda-san and the people. I don't know. I think this is the last one that Ueda-san and Mutakata-san are organizing. So I don't know if there'll be more after this, but we'll find out. And then Embedded Recipes is coming up in September in Paris. That's a kind of a smaller conference, a regional conference. Linux Plumbers is going to be in the US in November. And then FOSDEM has actually a pretty decent embedded track. And that'll be, the next one will be in February 3rd and 4th. That's not confirmed. Those dates are not confirmed, but that's the expected date. eLinux Wiki, that's been a big part of the community. We're losing funding for our administrator, Bill Trainer. And so the site is still used for a lot of useful materials for embedded Linux development boards. Academic, there are some schools that use it for their coursework. They actually have students put their projects on there. The primary purpose, I think, these days is for event materials. So we have slides and links to videos for ELC, for the Japan Jamborees, and for some other events sometimes. Um, Other areas of the site, I'll be honest, are often out of date. I still feel like the site is underutilized for information sharing. So the question was what to do next now that we're losing our funding. It may be able to kind of limp along. I actually talked to Bill. He may help us out, even though he's not getting funded. But if we could get some volunteers, if anybody is interested in helping us keep that site up to date and spam free, that's the main task. Let me know. In terms of other trade associations and projects, we have a huge number. So Linaro is doing ARM upstreaming projects and seems to be still going strong. There's the robot operating system that handles the robots vertical. It's all based on Linux. The Android open source project handles the mobile phone vertical. And there are also other projects in the phone area. There's Buildroot and OpenWRT that do build systems for embedded Linux. And OpenWRT focuses on the router vertical. Linux Foundation has a whole bunch of projects. The Core Infrastructure Project, which handles support longevity. So maintaining Linux distributions in the kernel for longer than 6 years, up to 10, 15, 20 years. ELIZA, which handles safety certification and standards. OpenChain and SPDX handling supply chain and licensing and SBOM issues. Automotive grade Linux handling automotive, kernel CI handling testing, Yocto project has a common build system for embedded. Drone code handles the drone vertical. And the core embedded Linux project, as I said, is shutting down. And it may not be needed because we have all these other projects that are handling certain things. So this all started as the Consumer Electronics Linux Forum in 2003. Migrated to the Embedded Linux Work Group, and then became the Core Embedded Linux Project, which is what it is still today. And we upstreamed a lot of technologies in a lot of different areas: Linux Tiny Patches, the SquashFS file system, and a few other file systems, real-time work, power management features. Actually started the Embedded Linux Conference and sponsored the Embedded Linux Wiki. And currently the plan is, I don't know if I'm making an announcement, I shouldn't be, but the plan is to end it in July. After 20 years of service, I think it's done a good job over the years, but there's a lot of other organizations that are tackling specific problem areas in Linux. Okay, so let me get to the scorecards. I'm actually over my designated time, I think. So I'm gonna breeze through these because I want to give you guys time to get on a train and get over to the Nakano Sun Plaza. So the original focus areas were system size, boot time, power management, real time, and security. So how are those doing? Well, if you base your analysis on contributions, it looks like we're done. I haven't seen a system size patch in well, except for the no-libc work that's gone into the kernel. I haven't seen a system size patch for the kernel for years. Same thing with boot time. Power management seems to be mostly done. Real time is almost all upstream. Security is in progress. So congratulations, we did it. World domination has been achieved. Actually, we have achieved world dominations, but I actually think it's a little bit more complicated than that. So system size, you could say we're done because we're not getting any more patches, but the lower limit on a modern system is about 16 meg, and it's not been getting any better. So we're not going to be running on those 1 cent processors that only have, 1 meg of RAM, or even less than that, 500K of RAM. So there's about 10 trillion IoT sensors will be running something else, which is a little bit disappointing, but Linux is being used in probably 95% of kind of the higher end embedded systems. Boot time, we're done. People don't work on boot time very much anymore, but people, not in the general sense, but they do. Some people do heroic special casing. So sometimes, like in the automotive for your backup camera, they'll do a lot of very, very hard, difficult things to try and get the boot time under a second or something, or under 5 seconds. But as a general thing, it's most products now, like phones or TVs, are using suspend resume or some low power idle. Power management, we've actually got a lot of support. Governors, frequency scaling, power domains, power quality of service, power scheduling, but it all requires SoC and board support. So this is now mostly a board support problem. It's not a general technology problem. Real-time, preempt RT code is almost all upstream. The only issue is that it requires ongoing maintenance to avoid changes that damage real-time performance. And kind of the same thing with security. Security you'll always have. As long as there are bugs, you'll have security issues that you have to deal with. So this is more the real scorecard. Where kind of most things are kind of done, but still need a lot of work, and boot time we could use. I realized after putting this all together that all of these areas require pervasive constant maintenance distributed throughout the code base. So to answer the question, well, let me look at the development side of things. I threw this slide in. If you look at how easy it is to develop Linux compared to the old days, wow, we're just killing it. So build systems, there's build systems galore, there's distributions you can use, training consulting, a lot of really good companies can help you out if you need professional help. Tool chains are all very high quality. The debugging capabilities are good. The languages are good. Test systems, we're working on those. Hardware support, we're working on that, but we'll always be working on hardware support. So my conclusion is, overall, we're doing really well. We're not done, okay? So it's obvious we're not done. But embedded Linux is widely deployed and functional on billions of devices. So we lost out to IoT. We're not gonna win the IoT devices. There'll be trillions of devices that won't be Linux, but that's okay. They can be Zephyr, they can be NetX or other things. But the core kernel systems are in place to support embedded. We'll always have things that we need to write and upstream, and the core code will always continue to get improved. So we're not done yet, but that's okay. That gives us job security, gives us jobs for the foreseeable future. So we can use Linux in our products and go forth and continue to use and develop embedded Linux. And with that, I will thank you for your time, and I appreciate your patience and your attention. So are there any questions? I'll go ahead and I think I'll make myself visible now.
Kim-san.
Yes.
Good evening. So I have just a comment. So regarding technical scorecard, I think those issues are have been handled for about 20 years.
Yes.
Yeah, they are very long journey. So, but it almost done. So.
Yes. Well, some things we decided. Actually, like on the system size is very interesting.
Yeah.
Like it would be great if we could run Linux on a 2 meg system, right? That would put us into a lot more processors. But you know, it turns out that like all the TVs and all of the cell phones and all of the routers, like, and even all of the small satellites, even things that are very, very resource constrained, can now have 32 meg or 64 meg. So we don't care anymore.
Yeah.
So we kind of the hardware solved that problem for us.
Yeah. Yeah, just a comment. So
yeah. Thank you for that comment.
Thank you.
Yeah, I think we cannot help to be something nostalgia about that kind of things. And Tim, you may find two questions from Kubota-san. One, that removal of the module license declaration means that all module will be GPL but version 2 only. That's his first question. And what is the difference between unknown and none? That is a risk in there. Yeah. That's two questions there.
Yeah. Okay, so let me look at this. Sorry. So no. So the removal of module license wasn't. So the removal of module license was only for code that was guaranteed could not be compiled as a module. So everything that still can be compiled as a module, which is a lot of drivers. So almost all drivers can be compiled as modules. You could either compile them into the kernel, or you could compile them as a module and load them separate from the kernel. what they did was they made it so that module, it's a long story, but people were using this macro module license on code that couldn't be compiled as a module. By definition, all of the code in the Linux kernel has to be GPL v2 only. Whether if it's in the kernel source tree, it has to be GPL v2 only, but it can be GPL v2 only and or another license. So if someone takes some code out of Linux and say puts it over to BSD, there are drivers in the kernel that allow you to take the source code and use the BSD license or the MIT license. Or there's about 5 or 6 other licenses. There's even some Apache code in there. And there's a weird new license that got in this year. I wasn't very happy about it, but so the answer to the first question is no, not all. Well, all modules are GPL v2 only, but several of them still have the or clause, or BSD or something else. So the code can be taken and used by other projects. And then what is the difference between unknown and none? So unknown is when we can't tell from, so what there is in the kernel source tree is there's a map of all of people's email addresses to what company they work for. And so that we can track the company, do those stats automatically. For some people, we don't know so some people it's obvious. So like when I contribute, I use the Sony.com address. So my email address says what company I work for. But some developers are not like that. Some developers are using Gmail accounts or some other accounts, even though they work for a company. And we know that they work for a company, so we have a mapping. But there are some people who we know, who we don't know, and then there's some people who, when it says none, those people, we know they're not working for a company. So that they're either hobbyists or we know that the code was contributed and it wasn't on behalf of their company. So that's the difference. So it's people we know are not working for a company versus people we don't know what their email address, who they're working for. So hopefully that answers that. Any other questions?
Okay. Thank you very much, team. And we'd like to move to another venue, that is Nakano Sun Plaza, which is about to be teared down because it's so old.
Yeah.
So
I just want to say I have very fond memories of coming to Nakano Sun Plaza in person. And I'm very sorry that I can't be there for this last one because I'm sure it would bring back a lot of great memories. Sure. So I wish you luck, and I hope you have a good second half of the meeting today.
Sure. Okay, thank you very much, team, and have a great evening.
Okay.
And just switched into Japanese mode. というわけで、今日の午前中のセッションはこれで終わりにしようと思います。今日の午後のセッションなんですけれど、2時から開始です。で、2時から開始で、場所は中野サンプラザか、さもなければこちらのオンラインか、いずれか、選択できます。で、いずれにせよまだコロナの完全に収まったわけではないんで、ウィズコロナの状態になっておりますんで、皆さんそちらの方の備えはして、サンプラザの方にお越しいただいても構いませんので、ぜひいらしてください。で、私もこれからちょっとカップラーメンか何か運んで、それで、中野に向かいます。で、おそらく、1時半ぐらいには私到着できる予定なんですけれど、その前に到着した人は、会館の方に行って、鍵を開けてもらってください。というわけで、皆さん、またお会いできることを楽しみにしております。どうもありがとうございました。では、一旦これで、中締めといたします。